now with the second type of inductance, which is a mutual inductance. So basically, mutual inductance is the fundamental concept that used in transformer basically, because if we base on this slide, if you have the same toroid, but both toroids are having different turns number. Let's say for the first turn having the current of I1, so then we have the N1 number of turns, and then we are going to have the secondary windings, which is having the N2 number of turns. So it can be said that from this I1 that is flowing inside the N1 turns, the flux will produce, the flux will produce from the N1 turns, and the flux will be linkage to the N2 turns. So the flux linkage in N2 turns, I mean in this particular secondary windings of N2 number of turns, we can see that the total flux linkage in coil 2, we call this as coil number 2. The total flux linkage basically shall be proportional to the current of I1. Okay, so this is what we call as mutual inductance, which means that the flux produced by I1 will be linkage to the secondary coil. In this case, is having N2 number of turns. So this is what we call as a mutual inductance, in which the flux amount or the total flux amount in the secondary coil or secondary windings, in this case is N2 multiplied with the flux amount. Basically we're going to have the flux amount N2 of psi M equals to M of I1. Basically we use the mutual inductance symbol as M. Self-inductance is L, but for the mutual inductance we use M. So basically the M or the mutual inductance will be simply N2 psi of M divided by I1. The same equation, the flux amount divided by I1. The difference is that N2 psi of M is basically the flux linkage. The flux linkage, which is the amount of flux that is produced at other side, produced by the I1 current or the primary current. Okay, so that is what we call as the mutual inductance. Mutual inductance. Okay, so I hope that you can now differentiate the difference between the mutual inductance and the self-inductance. So basically in transformer, the concept is based on the mutual inductance. Okay, so let's having this example number 3. We are having two single turn of coplanar concentric coils of radius R1 and R2, in which R1 is much bigger than R2. Okay, and R1 loop carries a current of I1 in clockwise direction. The question is determine the mutual inductance between the two loops. Okay, so that's the question, determine the mutual inductance between the two loops. Okay, so let us sketch this diagram. We are having two single turn coplanar concentric coils of radius R1 and R2. Okay, so let's just have this first one, then we have second one is here. Okay, in which given in the question here that this should be the R2 and that should be the R1, and given that R1 is much bigger than R2, much bigger than R2. Okay, and there is a current of I1 flowing in the R1, there's a current of I1 flowing in the R1 loop in the clockwise direction, so that should be clockwise direction. So the question is determine the mutual inductance between the two loops. So again, to find the mutual inductance, you need to find what? You need to find the flux produced by this current of I1 towards the R2. I repeat again, to find the mutual inductance is to find the flux amount that is produced by the I1 towards this loop of radius of R2. So that should be the psi M, and that should be divided by I1. Okay, so I repeat again just to make it clear for all of you. So M, the mutual inductance, is ratio between the flux M or the magnetic flux, in which Magnetic flux M here is the amount of flux which is calculated in this coil of R2, okay, yeah, and divided by this I1, which is the current that produced that particular flux, yeah. Okay, so we need to find the flux amount in which this should be based on the equations of B dot ds, yeah, the B dot ds, in which we need also to find, the mu not H dot ds. So we need to have information of the H field before we can find the flux. This is clearly shown from this equation, yeah. So you need to find out what should be the amount of H field produced by this I1. And luckily, we have done this previously in, I think, one of the questions that we did in Sahabat's law, yeah, Sahabat's law. If you can recall back, we find the, if I can recall back, yeah, you remember that we have a loop having current of I. We want to find the H field at this position along the axis. This is the axis, yeah, the axis of the loop. Yeah, this is I. Yeah, sorry. This is the line current, yeah, line current. We need to find the H field at its position, let's say position of 0, 0, Z. Yeah, remember what we did, we are using the Sahabat's law. Yeah, we have a H field at this particular location equals to integrations of I dl vector cross R over 4 pi R power of 3. Hopefully you can recall back, yeah, these things that we have learned previously in Sahabat's law. So if I can write it for you, we have just very short, yeah, very fast. I just go very fast here. So we have integrations of I. So the dl will be R. Yeah, in this case, yeah, this is R, yeah, radius of R. So that should be last time we put A or R, yeah, sorry. Yes, here should be A, sorry, it should be A, yeah, last time. So that should be A d phi, direction of phi, cross product with R vectors, which is A direction of negative R plus Z direction of Z, divided by 4 pi of A squared plus Z squared power of 3 over 2. Yeah, so end up we are going to have, when we do a cross product, yeah, we are supposed to get the equations of H field equals to I A. Let me see here. Okay, because this is a cross product. Remember that last time we ignored the negative R direction because of symmetrical effect, right? So we only have the Z direction. So basically, based on the cross product, we ignore or we cancel out the negative R component or real component. We just have the Z component in your answer. So basically, we're going to have A squared direction of Z, okay, divided by 4 pi A squared plus Z squared power of 3 over 2. And that should be integrations of d phi, which is from 0 to 2 pi. So end up we have the equations of I A squared over 2 of A squared plus Z squared power to 3 over 2 direction of Z. Okay, so that should be the answer that we have last time, yeah? Produced by this particular current, filament current of I, and having a radius of A towards a point of Z or 0, 0, Z. Okay, so the same thing is applied in this particular case. The difference is that we don't have any Z value, yeah, because it is just on a planar, yeah, on a planar plane, a planar surface, in which if we want to use this equation to solve this problem, basically the H field produced, yeah, need to change a few things here, in which your A shall be equals to R1, yeah, the radius of this should be equals to R1, yeah, you want to find the H field at the center, yeah, of your R2 radius loop, and the Z, which is the height, should be equals to 0. So when you substitute these two information into this equation, we're going to have H should be equals to I R1 squared divided by 2, and that should be 0, and we're going to have R1 power of 3 direction of Z. yeah, and then we're going to have I over 2R1 direction of Z, ampere per meter. Okay, so basically this is your answer. The H field produced by this particular loop having radius of R1, a current of I1, sorry, I put I1 here supposedly, need to have I1 there. And this is the amount of magnetic field produced to this particular loop, yeah? This particular loop, basically it should be at the center, of this point, yeah? Center of this structure, yeah, because if you base on this equation here, the equation is at the center of the loop. But if we base on the given information that the radius of R1 is very, very much large as compared to R2, in which we can then assume that if I stay here, if I at this particular point, yeah, if I stay here at this loop of R1 radius, I can just see that my R2 radius is just a single point. Yeah, it's just a single point because due to the reason that my radius of R1 is very, very much bigger as compared to R2. So I can just see R2 as a point. So we can just say that this H field basically is the H field or is the magnetic field that will be experienced by the loop of R2 radius. Okay, so based on this idea, we can then use the H field here to calculate the total flux that is actually trapped, yeah, in the radius of R2, which we can have that the flux amount in the R2 radius will be simply integrations of mu naught. H will be I1 over 2R1 direction of Z, okay, and my ds, yeah, I'm using this equation, yeah, and my ds shall be equals to r dr d phi direction of Z, yeah, because we are using the cylindrical system of coordinate. So based on that, if you base on this structure of rectangular, yeah, so your ds should be this ds on the top here, in which the ds here will be r dr d phi, yeah, and the direction should be following direction of the b, which is Z direction. So that's why we have the flux magnet will be b dot ds, in which b will be mu naught of h and the ds based on this equation. And as such, I can write that the flux amount per unit current, or I1, yeah, I bring the I1 to the left hand side, so that will be mu naught over 2R1 integrations of r dr d phi, r because this is deal with the radius of R2, yeah, this radius, so that should be from 0 to R2, and d phi will be from 0 to 2 pi. So end up I'm going to have that will be the mutual inductance, yeah, flux per current, so that should be my M, okay, and end up I'm going to have mu naught over 2R1 R, yeah, so let me see, yeah, okay, right, yeah, so we're going to have r dr, so that should be r squared over 2, so that should be r2 squared divided by 2, yeah, and that should be 2 pi. So end up I'm going to have can be cancelled out, pi can be, sorry, that should be in the cancellation, sorry for this, okay, so let me redo this, sorry for this, yeah. All right, so we have here will be r squared over 2, 0 to r2, that should be 2 pi, okay, so a few things can be cancelled out, 2 pi, so we're going to have mu naught of 2r1, so that should be r2 squared pi. Okay, so my magnetic flux, my mutual inductance will be equals to mu naught pi r2 squared divided by 2 of r1. Okay, so that should be my mutual inductance in Henry unit. Okay then. All right. Okay, any question for this calculation of the mutual inductance? So I hope that you understand that basic. Yes, yes.
The
Rehan.
mutual inductance is at the radius R2 or R1. This mutual
R2.
inductance.
R2. Because your source,
why we
the
have
source,
R1? May I know?
because the source of field is due to radius of R1, right? Your I1 current is flowing in the R1 radius. Okay, so mutual inductance.
Oh, okay.
So basically, the flux that we are calculating now is the flux which is trapped in the radius of R2. Yeah, so that flux amount divided by the current of I1, so that will give us the mutual inductance. Yeah, so the flux that we are calculating here, that we are having here, basically is the flux which is trapped. I can just put here trapped in R2 radius. Yeah, R2 radius. So I hope it's clear. Yeah, the flux that is trapped in R2 radius, which is B dot ds. Okay.
Okay.
All right, thank you for your questions. I think this will help others to understand more on example number 3. Okay, so we go for example number 4 related to this mutual inductance still. We are having a long straight lightning conductor lies in the same plane as a rectangular metal window frame. The window has sides of length 1 meter and 1.5 meters. The shorter sides are parallel to the lightning conductor and the nearest side is 0.5 meter from it. Determine the mutual inductance between the two circuits. Okay, let us sketch a diagram. We are having a long straight lightning conductor lies in the same plane as a rectangular metal window frame. Okay, so you have this is your long straight lightning conductor, which is same plane as a rectangular metal window frame. So window frame has sides of 1.1 meter and 1.5 meters. The shorter sides are parallel to the lightning conductor. So this is the shorter sides, which is 1 meter. Longer side is here. So basically, this is your 1 meter and this is your 1.5 meter. Okay, and the nearer side is 0.5 meter for it. So that should be the distance between the conductor and the metal frame, the window metal frame. So that should be 0.5 meters. Okay, so determine the mutual inductance between the two circuits. So I presume that the conductor is carrying a current of I. Okay, so that should be your current produced, that is exists in the conductors. So need to find the mutual inductance between the two circuits. So basically, we need to first understand the equation for the mutual inductance, where we have the M should be equals to the flux magnet divided by the I, the current. Yeah, so the flux magnet basically is the flux which is produced by the I1, by the current. So in this case, we have two circuits. The first circuit is your conductors, and the second circuit is your window metal frame. Yeah? So the flux amount basically is the flux which is trapped in this window metal frame. So this flux basically is the flux inside this window frame. And the I is the current that is producing it. Okay, yeah, so I hope you understand the concept of mutual inductance clearly based on this example. Yeah. So in order for us to find the mutual inductance, the first thing that you have to calculate is you need to find the flux. Yeah. So that should be based on integrations of B dot ds divided by the I. Yeah. So you need to calculate what should be the flux density that is available, or that is that exists inside this window metal frame. So you need to find the B, the flux magnetic B. Okay, so from here, we could know that the B shall be calculated based on the equations of mu naught of H. H will be I over 2 pi of R, I believe. Because this is based on a conductor. For a conductor of I, the H field produced will be I over 2 pi R straight away. And we can change this in terms of Cartesian system. If you assume that is Z direction, if I think that this is my Y direction, so I can just have that my B will be having a direction of will be in the direction of negative x, I believe, yeah, because x in this direction, yeah. Yeah, and the ds will be this one inside this unimetal frame, in which the ds vector should be equals to dy dz, yeah, dy dz direction of negative x, yeah, because we base on this y and z, yeah, right? So we can just write the ds should be dy dz direction of negative x, yeah, divided by I. So it can, if I can make a more modification to this equation here, I can just write r here as y, yeah? R as y. We just change r to be y because we assume that r is a distance, yeah? That should be my r. So this is alternatively equals to y, yeah? It's a variable, yeah? It's a variable because this distance, I mean this range here is parallel to the y-axis. So we just put y instead of r, yeah? I think we did this example before in calculating the flux, yeah, magnetic flux. So the same things apply. Okay, so that should be then proceed. We're going to have I can be cancelled out. So end up we're going to have the m shall be equals to mu naught over 2 pi. Okay, integrations of 1 over y dy, integrations of dz. So y is having a range from 0.5, yeah, 0.5 meter to 2 meters, yeah, because your y here is having range from this value 0.5 to this end, which is from 0.5 to 2, whereas z, the height will be from 0 to 1. So end up, we can have that the mutual inductance produced will be m as mu naught over 2 pi ln of 4 times 1. So that should be the mutual inductance in the units of Henry. Okay. So I think it's very straightforward on this calculation of the mutual inductance. Yeah. Okay. Any question on example number 4? No. Okay. So let us proceed with this example. Okay. So this is the example which is based on the previous exam questions. Yeah. So we are given a coaxial cable having inner conductor radius of 0.406 millimeter and outer conductor inner radius of 1.47 millimeter. We are given that the inner and outer conductors carry current I ampere in opposite direction. Insulator between the two conductors is Teflon with relative permittivity value of 2.0. So need to find in the Teflon region, yeah? So basically it is in the Teflon region. So that should be the region of interest. We need to find the flux density B, need to find the inductance per unit length, and we need to find the energy density. Okay, so let us sketch a diagram. So we have a coaxial cable. Yeah, that's your coaxial cable. Inner conductor is having a radius of 0.406 millimeter. And then we have the outer conductor inner radius. So we have, this is your outer conductor, but the inner radius is 1.47 millimeter, yeah, 1.47 millimeter. Okay, so that should be your structure, and the Teflon is here, yeah. The Teflon is here having a relative permittivity. I believe that this is not relative permittivity. It should be relative permeability, yeah. Relative permeability. I'm sorry for this mistake. I'm not sure why you did this mistake here. Okay. So that should be mu r equals to 2.0, yeah? That should be better than 2, yeah? Mu r, the Teflon inside this region between 0.406 and 1.47 millimeter, there exists a Teflon material with relative permeability of 2.0. Okay, so in this region of Teflon, in which if I can put the range R between 0.406 millimeter to 1.47 millimeter, this is your range of interest. Need to find the B. Okay, and it is given that the inner and outer conductors carry current I in opposite direction. So if I put that this is flowing in this direction here, so the outer conductor, yeah, this is the outer conductor, yeah, sorry for that. So it should be flowing in the other direction. So if we put that this is in the Z direction, sorry, if we assume that they should be in the Z direction, so that should be in the negative Z direction, yeah. Okay then. So based on this, I think it should be no problems of calculating the B, because you need to find the H first, and the H can be calculated based on the Ampere circuital law, I believe. Yeah. So the H dot dl will be based on the I enclosed, right? And this will be your Amperean loop, yeah, Amperean loop having a radius of r, yeah. And from here we can calculate that the H phi shall be equals to I over 2 pi of r. So H vector will be simply I over 2 pi of r, direction of phi. Yeah, because r here is any values between 0.406 to 1.47 millimeters. Yeah. Okay, and from here we can calculate the B straight away. So B will be simply mu naught mu r, okay, of H, which will be 2 mu naught multiplied with I divided by 2 pi r direction of phi in Tesla. Yeah. All right, so that should be your flux density B. Okay, so very straightforward questions. Yeah. Okay, and number 2, we need to find the inductance per unit length. Inductance per unit length in this particular region. Okay, so since we want to find the inductance in just in the Teflon region, which is between 0.406 and 1.47 millimeter. So to find the inductance, we need to find, we can use two methods. The first one is using the flux. Second one is using the energy. Yeah, energy. Okay, let us use the energy method. Yeah, so we need to find the energy within this region. Yeah, so we have half integrations of B dot H dV equals to half Li squared, correct? And we have calculated just now that the H and B in this region has been calculated. So we can just straight away find the L, in which L inductance will be simply B dot H dV divided by I squared. So that should be integrations of 4 of, sorry, I think I made a mistake here, sorry for this, yeah. Okay, so B times B dot H, so we're going to have 2 mu naught of I squared divided by 4 of pi squared of R squared, okay, and the dV, because this is based on cylindrical system, crystal cable, so that should be R dr dphi dz. Okay, so we're going to have L should be, can be cancelled out, so that should be mu naught over 2 pi squared I squared, and that will be 1 over R dr, okay, integrations of d phi, integrations of dz. Sorry, I forgot to put I squared just now, yeah, divided by S squared, yeah. Because if based on this equation here, the L should be the energy, so it should be the B dot H dV integration divided by I squared. So I need to put I squared down here. So that's why we have here I squared, right? And for range of R integration, we need to put the range as mentioned here for the Teflon region, which is between 0.406 to 1.47 millimeter. And dphi, because of full circle, so 0 to 2 pi, and length will be from 0 to L, yeah? And from here, we can find that the length will be simply, we can cancel out the I, yeah? Cancel out the I squared. Okay, so we're going to have mu naught over 2 pi squared, okay, ln of 1.47 divided by 0.406, 2 pi times L. Okay, so a few things can be cancelled out here. So 2 pi and this 2 pi can be cancelled out. So end up we're going to have inductance per unit length should be equals to mu naught over pi ln of 1.47 divided by 0.406 in Henry per meter. Okay, so that should be your inductance per unit length in the region of Teflon, which is between radius of 0.406 meter to 1.47 meters. So to test whether this answer is correct, so you can use the the first method that we have used before, which is to be based on the flux amount, yeah, in which the inductance will be based on the flux amount divided by the current of I. Yeah, so what you have to do is that you have to find the flux amount that exists inside this region between 0.406 to 1.47 millimeter. And then once you have the flux amount, you need to divide with the current I, and then you're going to obtain the inductance value of L. Yeah, so maybe you can test, yeah, maybe you can try to use this method and see whether the answer that you obtain is similar to what you have obtained earlier based on the methods of energy. Yeah. Okay, and I think for the third one, I think we don't have to proceed with this because indirectly we have answered this from question number 2 just now, which is this one. Yeah, the energy should be half integrations of B dot H dV. Yeah, B, yeah, this is not D, this is B, B dot H dV. So we have answered this earlier. So that should be the energy density that exists in the Teflon region between 0.406 to 1.47 millimeter region. Okay, is there any question on this example? Is that clear on this example? Okay, hopefully it's clear. Right, okay, so this example, I won't be doing it. Yeah, I think this can be done on your own because the concept is similar to what we have done before. Okay, basically the answer for part 5 here should be 0, yeah? To be 0 because this is to find the inductance at point P3 between the two conductors here. Yeah, note that the direction of the current are similar. So that's why the value of inductance is 0, yeah, because this is the argument that I mentioned in our example just now. Yeah, and I think for the actual inductance within the region of point P2 for the first case here, this diagram, I think we have done this also in our first example. So I think I don't have to proceed with this, but just to note that this is a sample of final exam questions which have been tested before. Yeah. Okay then.